Hi, everybody. So, Topher here, which isn't really my name, but I thought that was amusing. Elementary reactions and reaction mechanisms is what we're going to talk about next. So, mechanisms, it tells you the steps that it takes when the reaction takes place. Elementary reactions means simple. Elementary, my dear Watson, means it's simple. Elementary steps are the steps that make up an overall reaction. So, these are the easy one little bit, one little bit, one little bit. A slow elementary step, this is important, a slow elementary step determines the orders in the rate law. Okay, so that's how you get the orders. So remember when we're talking orders of a rate law, rate equals K, concentration of A, concentration of B. These would be my orders if I called this X and Y. Okay. Intermediates pull down the reactants above to add them to the rate law. And you got to kind of see that. That's coming up. Elementary reactions have one step. That means the entire reaction happens all at once. It's kind of rare, but it happens. This is the only time the coefficients are the exponents in the rate law. So this is the slow elementary step. Okay? Because normally we look at the coefficients of the entire equation, but the coefficients of the slow elementary step would do that. Higher order reactions are more difficult to execute, so they are more rare. Third order happens, not in AP chemistry, but it does happen. But it shouldn't be expected. So think a 5'9" guy dunking a basketball. That shouldn't happen very often. It can happen, but if you expect it, you're just silly. All right. Mechanisms must match the rate law and stoich. So what that means is if I have rate equals K, A to the X, B to the Y, what that means is my rate law has to be my coefficient of XA plus coefficient of YB yields whatever, and this is my slow step. And you might say, how do you know it's a slow step? It will be labeled slow. You'll be surprised at how clearly it's going to be labeled slow. All right, so given this reaction right here, this is not in your notes, so go ahead and sneak that in there. I don't know how it got chopped, but it did. So two mechanisms for this have been proposed. This one, Roman numeral 1 and Roman numeral 2. So let's see what each one would be if we have the following conditions. So what if A was true? Mechanism 1 with the first step is the rate determining step. If that was true, let's see if this is possible. I would have H2O2 plus I yields H2O2 plus OI. See how OI's cancel out? I have H positive on the left. I have HOI on the right. Oops, the HOIs are going to cancel out. Notice now I have two I negatives, right? I have two H positives, right? So let's see, anything else that cancels out? I2 cancels out. Does I3 negative cancel out? No. So let's see, if I add all this stuff up, I'd have H2O2 plus, oops, I forgot to highlight this guy right here, 3 I negatives plus 2 H positives would give me 1 H2O, 2 H2O, I3 negative. So 2 H2O plus I3 negative. So that's what I mean by matching the stoich, and that matches the stoich. So we're good there, okay? So mechanism 1, oops, it went away from us. Mechanism 1 matches the stoich, so far so good. If step 1 is the rate determining step, what would the rate law be? If step 1 was the rate determining step, I'm going to erase these things again and just focus on step 1. So all I'm going to look at is step 1. So in step 1, my rate law would be rate equals K. Oops, since it's erasing, I'll take a deep breath and I'll change my pen. So we can make it a little skinnier for this guy. So we'll just try it here. We'll do rate equals K H2O2 to the first, and then I negative to the first, because that's the rate law for these coefficients are 1. So that's how I put ones, okay? If the second step was the rate determining step, okay, second step is the rate determining step. Let's do that one in red. So with the second step, I have this right here, but do you see how OI is not in the overall reaction? So OI is going to pull down the next part. So that means for B, I'm going to have step 1, 1, and 2, okay? So that means I'm going to have rate equals K H2O2, because in order to get OI, I need to have all of this, okay? I'm going to rewrite that. I'm going to zoom in on this so I can rewrite it a little bit bigger for everybody. So we'll do rate equals H2O2. I forgot my K. Man, I'm struggling today. Rate equals K H2O2. Still need, whoops, I'm looking at the wrong one. H2O2, still need I negative. And now I've added H positive. So notice how OI does not show up in it because it cancels out. Okay? Because it cancels out, it won't be in the rate law, even though it's in that slow step. Okay? Rate determining step is a still slow step. All right. Mechanism 2 with the first step being rate determining. So let's clear out some space here and let's see if mechanism 2 matches the stoich, because if it doesn't match the stoich, it's going to be impossible. So let's take a look. I got H2O2. I got one of those. Remember, I'm looking for this balanced equation. I need 3 I negatives. Oops. H2O2, got it. I. Check. I need 2 H positives. Check. Check. I need 1 I3. Check, baby, 1, 2, 3, 4. I need 2 waters. And then I need the things that are left over to cancel out. Bye-bye HOI, bye-bye I2. So the stoich works for that one. So let's take a look at what C looks like. Uh-oh. So let's see what C looks like. Mechanism 2 with the first step rate determining. If that was the case, I'm going to have rate equals K H2O2 times I negative times H positive. So see how that first step would have everything in there with those coefficients of 1, 1, 1, 1, 1. D, mechanism 2 with the second step rate determining. Well, if the second step is rate determining, erase all these. The second step is rate determining. Notice how I have an intermediate in there, so I got to have all of those in there. So that means rate is going to equal an awful lot. So HOI is going to cancel out, but it pulls the other ones down. So I have to have K H2O2, I negative, H positive, but notice how I've got I negative twice, squared, H positive twice, squared. Okay, so that's what it would be. Now this one makes me think ugh, right? Because the order on this is 5th order, and I told you 3rd is extremely rare. So I don't think that's going to happen. But that's how you'd write them out, okay? Write the reaction and rate law for A through D above, which is what I just did. The rate determining, okay, so let's move on to the next part. So we're not going to do with E. The rate determining step is the slowest step. Imagine a reaction occurring moles of time. So that means 10 to the 23rds of times. That's a lot. The steps have to wait for the slowest step. The slowest step would be labeled slow. Okay? So this is my overall reaction. That's my slow step. Or it would give you a mechanism that would say slow, fast, fast. Okay? How do you know what the slow step is? It's labeled slow. Okay? So when I was in the ever popular 6th grade basketball, there was the slow jersey. So whatever kid was the slowest kid when we ran sprints had to wear the slow jersey. It was labeled slow. It was an article of shame. You probably can't do this anymore. But everybody would fight to make sure that they did not have the slow jersey. So they tried harder and worked their butt off, and it really helped the bottom end of the team to make sure they didn't have to do this. Okay, this is just a rehash of the collision theory, which we did before, but we're going to do it again. Collision theory, just to emphasize how important this is. Here we go, again, again, again. For a reaction to be successful, particles must collide with enough energy, and they must collide with the right orientation. You need to have all of these, not some, all of them. Okay? Successful reactions are rare. So imagine if my reaction is throwing a ball and a mitt and both of them in the air and having it catch and stick. 1 out of 10 million is not uncommon. That's rough, man. That means it's almost never going to happen. That's kind of sad. Reactions involve bond breaking and bond forming. So barf, remember, breaking bonds absorbs energy, releasing energy forms bonds. And then we have Boltzmann diagrams. So here's a little Boltzmann diagram. We talked a little bit about activation energy. The shaded area is the only part with enough energy for the reaction to occur. That means still maybe not. Right? Still maybe not. So if I said Isaac will date anybody, well, no, Isaac dates living people. If someone's alive, that doesn't mean Isaac's going to date them. They still might not, right? So this is just the ones that could possibly do it. Catalysts move the line to the left. So if I add a catalyst, what that does is it makes the line shift to the left. So now there's even more eligible particles to react, right? So that means the reaction will go faster because more particles have enough possible energy. The Boltzmann diagram shows essentially temperature. Hotter diagrams are lower and brighter. So remember, this would be hotter. Colder diagrams are higher peaked and lesser. Okay, so if you look right here, do you see how making it hotter would give you more, particles with enough activation energy? And if you're colder, you have way less. Okay. All right, that's it. 11 minutes half. I'm out of here. I'm Topher, and I'll say bye.